We're going to revisit now the concepts that we learned in our previous two videos in the simple case of an investment universe where there's only two risky assets and a risk-free asset. We focus first, as we did earlier, on portfolios of risky assets only. Consider portfolios of the two available risky assets, which, just for the sake of giving them a name, let us assume that they are the shares of two companies, Spin and Bang. The return of any of these portfolios is equal to the weighted sum of the returns of these elements, where the weights are the portfolio weights. These weights have to add up to 1, and thus we can write the weight on Bang as 1 minus the weight on Spin. Also, the expected return of any portfolio P is the weighted sum of the expected returns of the elements of the portfolio, where again, the weights of this weighted sum are the portfolio weights. Recall that the variance of the portfolio has this formula in the simple case of two assets, where we can again write the weight of Bang also expressed as 1 minus the weight on Spin. The standard deviation of the portfolio is just the square root of the expression for the variance. Suppose that the expected returns, variances, standard deviations, and covariance associated with our two risky assets are as given in this table. Any specific portfolio of these two risky assets is obtained by fixing the value of the weight on the stock of a Spin. The expected return of the associated portfolio is given by that expression, and the standard deviation is given by this other one, as we know. For example, if we choose a weight on Spin equal to 0, the weight on Bang is equal to 1. And this implies a portfolio where all our investment wealth is going to Bang. And hence, the expected return and standard deviation of the portfolio are just the ones of Bang. Another possible choice could be a weight on Spin equal to 1. This implies a trivial portfolio where all our wealth is going to Spin. The expected return and standard deviation of the portfolio are just the ones of the Spin in this trivial case. Another portfolio can be obtained by setting the weight on Spin equal to minus 0.1. This means that we sell it. The weight on Bang would be greater than 1 and equal to 1.1 in this case, meaning that all our investment wealth is placed on Bang plus an additional 10%, and that additional 10% is financed by selling or short selling the stock of Spin. Another possible portfolio is obtained by setting a weight on Spin equal to 1.1. This corresponds to an investment where all our wealth is going to the stock of Spin plus an additional 10% of it. This additional 10% is financed by selling or short selling the stock of Bang, whose weight is thus equal to minus 0.1. We could obviously also consider portfolios which imply a strict positive investment in both the stocks. A weight of 0.45 or a weight of 0.31 in Spin are examples of this. If we illustrate in a two-dimensional graph the resulting expected return and standard deviation for each chosen weight, where the vertical axis displays the expected return and the horizontal axis of standard deviation, the point corresponding to a full investment in Bang will be right there. And the point corresponding to full investment in Spin will be right there. Sweeping over all possible values for the weight of Spin, we can find all other possible points, and they will sit on a curve like this one. Any point in here will correspond to straight positive investments in both stocks, that is, weights between 0 and 1 for both stocks. Points in here will be associated with weights on spin greater than 1. And points here will correspond to weights on spin less than 0. It is important to note that in this very special case where there is only 2 risky assets, the frontier and the opportunity set are identical. In other words, there are no points over there. An important element is the one associated with the minimum variance portfolio, the MVP. How do we find the actual weight on spin for this point? Well, we know that the MVP is the one that has the smallest variance. Hence, we need to find the weight on spin, that is the value xs, which minimizes the expression of the variance. If you recall your high school mathematics, that is done by computing the first derivative of this function of xs and setting it equal to 0. After doing some algebra and factor out xs, you will see that the value of xs must be equal to this expression in such case. Do not worry, you will not be expected to know how to obtain this expression. Just trust me on this one. Bringing back again the table displaying the variance and covariance of a spin and bang, we can plug them into the expression that gives the weight of the MVP in this case. And when we type these numbers into our calculator, the resulting value of the weight of the MVP is equal to 0.31. This value of the weight was already presented in the table, and you can do the calculations if you want to find that the spectral return and standard deviation of such portfolio are equal to 10.6% and 11.2% respectively. We can now show those values in the graph. Now, if we begin reasoning as we did in the general case presented in a previous video, we can see that a full investment in bang, that is the point B, is dominated by the MVP, in the sense that any investor with the preferences that we have assumed all along will always prefer it over B, because it has a higher spectral return and a smaller standard deviation. But the same can be said about any point in the frontier sitting below the MVP. Hence, all these points are inefficient portfolios. The efficient frontier is the remaining part, that is, the one that contains all the points in the curve above and including the MVP. If we add a risk-free asset to the investment universe, we can now build portfolios whose elements can be the resulting 3 assets. Any such portfolio can be constructed as a portfolio of that portfolio of the 2 risky assets and the risk-free asset. From a previous video, we know that in this case, the efficient frontier becomes the capital allocation line, which is tangent to the efficient frontier of risky assets only. If we assume that the risk-free rate is equal to 6%, we can now present this efficient frontier of all 3 assets in the graph. The point T, that is the tangency portfolio, is the portfolio of 2 risky assets whose capital allocation line is tangent to the efficient frontier of risky assets. So the tangency portfolio satisfies that its capital allocation line is the one with the highest slope out of all the capital allocation lines which can be built with a portfolio of the 2 risky assets available. We know that the slope of any capital allocation line is equal to the Sharpe ratio of the portfolio of risky assets used to build it. Hence, the tangency portfolio of a given investment universe can also be defined as the portfolio of risky assets with the largest Sharpe ratio. How do we find these weights? Well, recall that the Sharpe ratio of any portfolio P is equal to the ratio of its expected return minus the risk-free rate divided by the standard deviation of its return. Hence, we need to find the portfolio of the spin and bang for which the Sharpe ratio is maximum. That is, We need to find the excess, that is the weight on spin, for which this animal is the largest. Once again, your high school mathematics will tell you that you need to find the first derivatives of this expression with respect to xs, set it equal to 0, and solve for xs. When you do that, you find that the weight on spin is equal to this monstrous expression. Do not freak out. Proving all of this is beyond the scope of this course, but you will again have to trust me on this one though. Bringing back the table with the spectral returns, variances and covariances, and recalling that the risk-free rate is assumed to be 6%, we can go ahead and plug into the expression of the weight of the tangency portfolio the corresponding ingredients of our case to find that the weight is equal to 0.45. This value of the weight was already presented in the table, and you can do the calculations if you want to find that the spectral return and standard deviation of the tangency portfolio are equal to 11.3% and 12% respectively. Values that we can now show in the graph. This is all for now. See you soon.